So welcome to the lecture. First, some announcements. Concerning the assignments, questions about the theory assignments you can send to me and not to Sarbojit. But questions about the labs, you should send to Sarbojit. But please try to CC me also in case there is something which I would like to answer myself also. So this is more convenient for us like this. And I also would like to say that there will be no lab on Friday, but instead we'll replace one of the lectures next week by the second lab. So there is a lecture on Wednesday, no lab on Friday, and then next week one lecture and one lab. And I will announce which lecture we will change to a lab later. So this is it's an overview of the course again, and you see the topics that we have covered, the overview with definitions of safety, liveness, properties, abstract data types, sequential programs, and by now you should know these things quite well. So I will just skip these topics today, and I will start from concurrent programs and recall some of the concepts. So the basic ingredient in the analysis of the behaviors of concurrent programs is the notion of a concurrent history. So here we have a typical example of a concurrent history, and you see that you have method calls, and these method calls, they overlap. So this means that some of them will start, but you can initiate other calls while some calls are still ongoing. So this means that you get an overlapping. So if you look at a concurrent history, you have two types of relations. First, you have the calls that precede precede each other. This means that the first call ends before the second call starts, and then you have what we call overlapping calls, like these two calls here. And this was the first step in defining our notion of linearizability for concurrent histories that transform concurrent histories to sequential histories. So these were these two notions that I mentioned. First, you have precedence, where you say call one precedes call two if call one ends before call two starts. Or, let me see the chat. Okay. Call one precedes call two means that call one ends before call two starts, or the interval of call one precedes the interval of call two. So here we have an example of two such calls, where the green call here precedes the red call here, because this call here, if you look at the response of the call, it happens before the initiation of the second call. So this one ends before this one starts, and therefore we say that this one precedes this one here. Call one, the green one, precedes call two, the red one. And we have the notion of overlapping, where the calls overlap. So here we have an example of two calls that are overlapping. And we say that in our interpretation of a concurrent history, we reason about linearizations. And linearization means that you linearize the calls such that if one call precedes the other, then the same thing applies in the sequential history that you generate. So to do that, we define the notion of linearization points, where a linearization point is that a point, or you select a point inside inside the interval of some call. So here we have the initiation, and here we have the response, and here we have the linearization point of this particular call between the start and the end. And this you can apply to all the concurrent calls inside the concurrent history, and in such a way you obtain a linearization. So now I can consider these overlapping calls as sequential, because I can order them according to the order on the linearization or the linearization points. So I'm given a concurrent history H, I define a linearization points, and in such a manner I order the concurrent calls, as I have done here. Now, this definition of linearization or the linearization operation has a nice property, namely it guarantees that if some call precedes another call, then its linearization point by definition will precede the linearization point of the second call, as you see here. Because there is no way, because by the requirement that I put a linearization point inside the interval of each call, there is no way I can put the linearization point of the green call here after the linearization point of the red call. So this means that this is a natural way to impose a linearization of these concurrent calls so that you preserve the precedence relation. And also because we say that overlapping operations or overlapping calls are not ordered, then this is also reflected in the definition of the linearization points, because we allow a linearization point to be anywhere inside the interval. So if you take these two intervals, for instance, then by shifting the linearization point of the green call to the right and the one of the red to the left, then you obtain a different order in the linearization points. So here we have a situation where we have defined our linearization points. So we are given our concurrent history. Now we define a sequential history H prime, which is in the set of linearizations of H. And we do that by taking the concurrent history and define the linearization points as we wish, provided that each linearization point is placed inside the respective interval. And now we consider the order of the linearization points according to the order of, or we consider the order of the linearization points, and based on that order, we order the concurrent calls. Yes. So in this case, we have number 1, number 2, number 3, 4, 5, and 6, and this gives me this order on the calls. So you see that I have generated, given a concurrent history H, and given the linearization operation, the placement of the linearization points, I generated a sequential history H prime, in which I order the calls now according to the order of the linearization points. So this call first here, this one is the second, this one is the third, the fourth, and the fifth, and the sixth here. Okay, so in such a way, we have defined one linearization of the concurrent history, which is a sequential history. So, and this is the property I mentioned before, namely, if call 1 precedes call 2 in the original concurrent history, then regardless of how you define your linearization points, where you place them, call 1 will precede call 2 in the generated sequential history H prime. So this applies, as I said, for these two calls, for instance, and also between this one and this one. But on the other hand, if you have overlapping calls, then you don't know, there is no requirement. So now by taking this particular order of 1 and 2, you have this order in the generated sequential history. But if you, this is the order reflecting this order, 1 and 2 of the green and the red. But if you swap the linearization points, then you get a different order in which the red comes first. So the precedence relation is preserved by applying the linearization operation. So now, having transformed the concurrent history to a sequential history, we can go one step further, because we know how to transform a sequential history to a trace, which we do by the collapsing operation, in which we collapse the call or the initiation of the method with the response. So add 2 true here, add 7 true here, etc., etc. So from this concurrent history, we got a sequential history H prime by linearization. From H prime, we got trace tau by collapsing. So now we can go back. So we can see that, okay, I know that tau is a trace of H prime, as we defined it in the previous lectures. And because tau is in the set of traces of the abstract data type set, I can conclude that tau is, or H prime rather, is in the set of histories of the abstract data type set. So this follows from these two properties. Now, because I know that the sequential history H prime is in the set of histories of the abstract data type set, and because I obtained H prime by H through linearization, then from these two properties, I say that H is linearizable with respect to the abstract data type set. So in this way, we can reason about correctness of concurrent programs by transforming the concurrent histories they generate to traces which we can check to be member of the set of traces of a given abstract data type or not. Okay, so this was linearization, and this helped us to explain the validity of some histories. So for instance, we said that this is linearizable with respect to set, because there is a linearization, namely this one, which gives you this sequential history, which in turn is in the set of histories belonging to the abstract data type set. Applying the same reasoning, we can conclude that this is not linearizable. This concurrent history is not linearizable with respect to the abstract data type Q, because regardless or however you put your linearization point, you'll violate the operational behavior of Q. So by giving this framework to reason about concurrent histories and judging or defining the criteria of concurrent histories being linearizable with respect to a given abstract data type, we can now turn our attention to concurrent programs. And this is a typical example of a program implementing a concurrent data structure, in which you have the data structure in the middle, and in which you have different threads, 4 threads in this case, each one of which is manipulating the data structure, which is said in this case, using a set of modules, each reflecting one method. So for instance, here we have the red thread, and here we have the module implementing the method contain. And you see that now the methods will overlap, because you may generate a method call by giving the method name and the input value, and then you the same thing will happen with the green thread, for instance. In this case, they will overlap. They change the state of the data structure, and then they get their answers eventually from the data structure. And in such a way, you generate a concurrent history for the program. So in fact, here it's important to notice that the method implementation is 2 parts, namely the code that implements, or the module that implements the method, but also the linearization policy, that is the definition of where your linearization point is. Okay, so we started with the first concurrent algorithm, namely coarse-grained locking. And the idea was simple. It was just to take the naive implementation that we have for a sequential program that implements the abstract data type set, and putting a global lock on the data structure. So a lock is, if you wish, a variable that can be acquired and released, and which can be acquired at most by 1 thread at a time. So for instance, you may have the red thread which has the lock, but at most 1 thread has the lock at a point of time, or you may the green have the lock, or when I draw the lock as black, then this means that the lock is free. So given this, we generated, or we studied a program, first naive program that implements a set concurrently. What we did was that we took the lock and put it before and after the sequential code that we already had to implement the given method for sets. So for instance, for add, we have the sequential code, and then we put the lock before and after the code. So this means that if a thread wants to perform an add operation, then it has first to acquire the lock, perform the operation, and then release the lock. So this gave us something like this, where we also defined the linearization point, and we say that we define the linearization point in this case to be the point of time at which you acquire the lock, and this would be good enough. And in fact, it was quite flexible in this particular example where you choose your linearization points. Only it's between the lock and the unlock, because no thread will interfere with the given thread when the thread has access to the lock. So this was our linearization point, and then we applied this idea. For instance, if you have two threads that are trying to add or perform operations on this data structure concurrently. So for instance, you have the red thread trying to add a 4 to the set. Then you first acquire the lock, so it is red now, so nobody else can access the lock. And then you define your linearization point at the same point as the point where you acquire the lock. And then you perform the execute the code as usual. You have these 2 pointers, previous and current, that you will reuse in different algorithms. And then you take your while loop here, which takes you to the relevant position in which you insert or try to insert the new key 4. And this is the position in which, or the point at which you observe the first key, which is not strictly smaller than your key. So if I'm adding a 4, I look and search the list and find the position in the list where I have the first key not smaller than my key, which is the 5 here. And now I insert the 4 in between. So I check that the value is there or not. In this case, it's not there because 5 is different from 4. And therefore, I insert a new node with the key 4 in between 3 and 5. And I maintain the invariant. The list is still sorted, but I have now successfully added 4 to the list. And this is done by, this means that we return the value true to the caller. And finally, we unlock L like this. And the operation terminates and the lock is free again. So now you may have 2 threads operating in parallel. So if you have the red thread starting and then the blue thread starting. And then now the question is, there is contention because each one of them will try to obtain the lock. So in this case, the red succeeds, which means that it takes the lock first, and then it linearizes at the same point where it took the lock, acquired the lock, and then it executes its code, which we know now it will insert a 4 between 3 and 5, like this, and then it unlocks, and then it terminates returning true because the operation was successful. So now the blue one will do the same thing. It acquires the lock, it linearizes at the same time, like this, and then it performs its code, and it inserts a 2 now between the 1 and the 3 in the new list. So you get something like this, after which it unlocks, and it terminates. So now you got a concurrent history in which you have 2 add operations, and in which the red one linearizes before the blue one. And the definition of contain and remove are exactly the same. Namely, you have the sequential part of the code that we know well by now because the subject of the first lab. And then you have the linearization points where you have the locks or the acquire operation on the lock. And then you put the lock and the unlock before and after. And we will consider these codes like this. I will not go through the details of the code. So now we can run several processes or threads together. So if you start with the empty list, we have 4 threads manipulating the list or the set. So for instance, the green starts first, and then the red and the yellow. And now there is contention between these threads on the lock. So one of them will succeed in taking the lock first. In this case, it's the yellow one. So this means that it linearizes at the same point at which it acquired the lock. And then it looks at the list, and we know that it will return false. So it releases the lock and returns false. So then the red thread will take the lock, and linearizes at the same time, and it tries to add a 7, in which it will be successful because you don't have a 7 inside the list, and then it releases the lock, but it's not terminated yet. So now the green will take the lock because the lock is empty. So now the lock is green, it linearizes at the same time, it tries to add 2, and it will be successful because 2 is not inside the set. It releases the lock, and it terminates, returning true. So red has still not terminated. And then the blue thread will become active. It tries to remove 2. It takes the lock, and then it removes 2 successfully. And now you perform more steps, and you get a concurrent history, which is like this, which you went through in the previous lecture. So you see here that you have threads that are running concurrently, and in this particular case, it's an essentially sequential behavior in the sense that the method calls, they are overlapping, but at any point of time, at most one thread has access to the list, and therefore at least at most one thread can manipulate the set. And we say that this program is linearizable because if you take any of its concurrent histories, then you can find the linearization in which the resulting sequential history is a member of the set of histories of the abstract data type set. And then we went through the coarse-grained synchronization algorithm. Advantages, it's simple, as we saw, because you just take your sequential code and you put locks before and after each method code. It's essentially sequential behavior, so it's easy to reason about it, and it was easy to conclude that the program indeed was linearizable with respect to the abstract data type set. It's efficient if you have low contention, that is, there are not many threads competing for the lock at any given point of time. But this is a big assumption, of course, because typically you'll have many threads competing to access the data structure. It's correct from the point of view of safety. We say that we would look at linearizability in this course. And liveness has a good property. Namely, it preserves the same liveness guarantees that are given by the lock. For instance, if the lock is lock-free, in the sense that at any point of time, if there is a request to access the list, then at least one of these requests will be performed. So in such a case, the whole algorithm will be lock-free, and the same applies for weight freedom. Disadvantages is that it is inefficient if you have high contention, which is the typical case. And the reason is that exactly the reason why it was simple, because its behavior is essentially sequential, which means that if you have a lot of concurrency, then you will not be able to exploit it in the algorithm. This is efficient only if you have low contention. And one more remark that we had is that actually this is quite simple, and in fact the choice of the linearization points is not important. Only you respect the property that it's between the point where you acquire the lock and the point where you release the lock. Okay, so all these things, or in fact the inefficiency of coarse-grained programming brought us to coarse-grained locking, or coarse-grained synchronization, or no, to fine-grained synchronization rather. And we say that the philosophy here is that to increase the concurrency, because we have concurrent data structures after all, and our job is to increase the degree of concurrency and in such a manner to obtain more efficiency. And the idea is that not to lock the whole data structure as we did in the coarse-grained algorithm, but to lock individual cells. And the strategy to guarantee correctness here is that what we call lock coupling, or hand-over-hand lock acquirement, which means that you acquire the lock for the next cell before you release the lock for the current cell. So, and in order to implement that, now we put the locks inside the cell. So this means that you have many locks, namely one lock per node, and you have the key, the next pointer, and the lock is free, or it is busy, taken by some thread red in this case. So this is the strategy for the algorithm, and concretely, what you do here is that you see that I don't have a global lock, but I lock locally. So this means that I lock H first if I want to add 4. So I lock H, and then I lock, I create the pointers as usual, previous and current, and then I lock C. So I have 2 cells that are locked. So like this. So this is my PNC, and then I have 2 cells because I lock C here. So I have 2 cells that are locked. Now, once I have done this, now I have defined an area of operation in which I will not be disturbed by other threads. So now I look for my key. As usual, I do the locate procedure, but I take these 2 locks with me. And always we have the hand-over-hand lock acquirement, which means that I may release the previous lock, but I will not release the current lock before I have acquired the next one. So this is what the while loop does for you. So you look inside the list for the location to put your key for, which is again the first key, which is not strictly smaller than your key. And what I do here is that first I unlock P, as you see here. But then I lock C, I move the 2 pointers P and C, and I lock C before I release this one. So you see that here, when I go back to the while loop, I still have 2 locks. And this is what we call hand-over-hand lock acquirement. So now I release this one and then take the next one until I find the position in which to insert my key, which is in fact this position here. So I add the 4, as usual, creating a new node and then redirecting the pointers. I get something like this here, where I've added the 4 to the list. And then now I can return through and unlock the C and the P because I have finished my operation like this. So you see that everything now is unlocked and the list is entirely free. Okay, so now we can have 2 threads that are operating on the same list. So again, there is contention between the red and the blue for the first lock, which is the lock of H. So now in this case, the red will succeed. And now it does the same thing. It does this lock coupling, locking the first 2 cells, and then looking for the correct position in which to insert the key, which is the 6 here. So it should be inserted here. So you see that I take my locks with me and I go to that position. So in fact, these cells are now free. So you see that the blue one can start working, and it will lock the first 2 cells and put its 2 pointers on the first 2 cells. So now you see that we have 2 threads that are working concurrently inside the list, but they are working in different places inside the list. And this is the whole philosophy with this algorithm, that why prevent threads from entering the list if they, after all, work on different parts of the list and they do not interfere with each other. And this is what happened here. So now, in fact, the blue one has immediately found the position in which to insert its key, which is the one which it should be put here. So now the red one will become active again, and it will insert its key to the appropriate position. And now the blue one may become active and insert its key into the appropriate position. And then the red one becomes active and it unlocks its locks. So it becomes like this. And finally, the blue will become active and it unlocks the locks of the cells pointed to by P and C. And now we get something like this. So in this case, in fact, the red took effect before the blue. And this will be more precise when we define our linearization policy for this algorithm later today. So now if you go back to the initial scenario, it can also be the case that when you have contention on the first cell, the blue one will go first. So for instance here, now you see that what it will do is that it locks the edge. So now this is one disadvantage of this algorithm. If a thread operating on the left side of the list goes first, it will block the threads that are trying to operate on later parts of the list. So in this case, the red cannot enter the list before the blue has finished. So the blue will work like this as usual. Put your pointers PNC on the first two cells and lock them, and then look for the position to insert the key, which is the first position here, and put it there. So still the red is trying to enter, but unsuccessfully because this lock is taken and it has to acquire this lock before it can do anything. So now it has to wait for the blue to return. It returns through, it unlocks C and P, and now the red is free to go there. It goes there, locks the first two cells, and then it goes for the position to where to put its key, which is the 6 between these two, and then it puts it there, like this. So what we got was that in these two scenarios, in the first one, the red one took effect first, or linearized, as we will see later, first before the blue, while in the second one, it was the opposite. So now in this case, the red finally will unlock itself, and now the full list is free. Now, if you look at the remove operation, it's exactly the same. So now you recognize this piece of code, and this is why I said in the first lectures that although it is very simple, it will be important because by simple variations of the code, we get quite different concurrent algorithms. So here, if you have removed, it's the same thing. You lock the first two cells, and then you get to the position where you find the key, the first key, which is not smaller than your key. So you are trying to remove 5, and 5 is this first key, which is not smaller than 5. So all the time you are locking 2 cells at a time. And then now what you do is that, as usual, if the key is inside the list, then you succeed in removing, and do that by redirecting the pointer of the cell pointed to by P to the cell which is pointed to, or the next cell of the cell pointed to by C. So you get there, and this is what will happen. And then you return true, and then you unlock your cells. Okay, so then for the contain, I will leave it as an exercise, and maybe it will be the subject of the second assignment, by the way. So the second assignment will be uploaded sometime later this week, and it will be related to these lectures about fine-grained, and then also optimistic and lazy synchronization, which I'll go through today, and on Wednesday, and then early next week. So the important property of this algorithm is lock coupling, as we mentioned. So what lock coupling means, if you look at it at this high level, is that you have these two sentinel nodes, H and T, and then you start searching the list to find the first key, which is not smaller than your key. And all the time you acquire the next lock before releasing the current one. So for instance, if you have a thread, the red thread trying to remove 4 from the list, what it will do is that it locks the first cell, and then the second cell, puts its pointers there, and then it will go through the list to see whether 4 is there or not. So it will release the block of the cell pointed to by P, and then it moves 2 pointers. It's 2 pointers, 1 step forward. It acquires the next lock, which is this lock here, and then it continues, releases this one, and then moves the pointers, and then acquires this lock. So you see here, until I find the first key, which is not smaller than mine, which is here. So now I perform the operation because I did find this element here, and I redirect the pointers like this. So now let's take a similar scenario in which we have two threads that are trying to compete to remove two elements concurrently. So you see what's happening here is what I pointed out in the previous slides, is that you see that each thread operating inside the list always has some operation area which is protected from the other threads. So you have this thread here, the red one, and it has its two cells here, and nobody will be able to enter this area while the red is there. And by the same token, the red will not be able to enter and interfere with other threads. So this means that any cells taken by some threads inside the list, they are not so they are not possible to enter by other threads. So you may have different threads operating concurrently inside the list, but nevertheless, all of them will concurrent in different positions, and therefore they will not interfere. So you have this notion of locality in which the threads operate. So threads cannot overtake each other. This is an important property of the algorithm. So, and therefore they cannot interfere with the operations of each other. And therefore, this is how you achieve correctness. So in fact, what you have is that lock coupling implies that there is a barrier just before the cells taken by each thread. So this is the barrier for the red thread. And this implies that the blue can never overtake the red, well, never, I mean, in this operation. So once a thread is inside before some other thread, then it remains inside until it finishes its operation. So here the red entered the list before the blue, and therefore the blue cannot overtake the red. So this means that the red must finish before the blue can do its operations, if the operations of the blue thread are beyond the area of operation of the red thread. But on the other hand, if the blue thread is operating here, then it's fine. It can change these cells. And in fact, this will be the subject of one of the tasks of the second lab, where you try to study fine-grained synchronization, but having different types of threads that are competing on different parts of the list, or on the same parts of the list, or similar parts of the list. Okay, so now this is a general observation. You have barriers for each thread, and such a barrier cannot be overtaken by other threads. So this means that you have an area of operation for each thread at any given point of time, in which the other threads cannot enter. And this means that the red thread here can operate peacefully in that area. So if it wants to insert something here or remove one of these cells, then it can do that without risking the incorrectness of the algorithm. So the same thing applies for the blue thread. In fact, it has taken the first two cells here. So you observe that if there are threads waiting outside, they cannot enter. So it cannot be overtaken. So once you are inside, you have locked edge, nobody can overtake you later. So this means that if you wish, you can view this algorithm as some kind of pipelining. So you are pipelining the threads inside the list. They do their operations, and then they leave from the other side, leaving room for the other threads to follow in case they wish to do so. So this means that other threads cannot overtake the blue thread, and therefore it has its own operation area. And the same applies for all the threads. The green thread here has its own barrier, cannot be overtaken by other threads, and therefore it has its own operation area. So this is a typical configuration. Although in practice, of course, you may have hundreds of thousands of threads operating at the same time. But by keeping a track of this invariant, you see that nothing bad will happen from the point of view of safety. So the operations, and this will be reflected when in the linearization policy of the algorithm, which guarantees correctness with respect to the abstract data type set. And also one other thing which I would like to emphasize here is that although we are implementing these strategies like fine-grained synchronization for sets, it can equally well be applied to other sequential implementations of other data structures like stacks and queues in such a way turning them into concurrent implementations that guarantee linearizability with respect to the given abstract data type. So in general, this is what we have in this algorithm. We have these areas, and the threads are operating in different areas of the list and therefore not interfering with each other. So I think I will stop here before the break. So if you have any questions, please ask now, or you can put it in fact in the chat and I will answer them after the break. So see you 1/4 past. Thank you.